All right, in this last video in section 14.4, we're going to look at question 6. It says to consider the solid region E, which consists of all points x, y, z, where z varies from 0 to 1 minus y varies from the square root of x to 1, and x varies from 0 to 1. And we're provided this figure here. Our job is to set up iterated integrals for the triple integral of a generic function f over the region E in the orders dz dy dx and dy dz dx. Okay, so just a couple comments about the figure first. This flat portion, this face of our wedge that we're seeing here, this is just a part of the plane z equals 1 minus y. And then this curved portion here is part of this parabolic cylinder y equals the square root of x. So if I look at the cylinder on its own, we're going to see this kind of a shape. So think about just taking the square root function, and then since this equation is independent of z, we're just copying the square root function as we run parallel to the z-axis to form the cylinder. And now this plane, z equals 1 minus y, is going to slice into our cylinder. Think about lopping off this top portion, and then we have that face formed in the first octant by the plane. And then the base is just where we would lop off on the bottom there with the xy plane to form the base of the solid. And then we have the backside there, which is just that triangular face. Okay, great. So now let's set up the triple integral as an iterated integral in the order dz dy dx. Okay, so we're going to let z vary first, and then think about x and y as being fixed. And let's first, before we set up the bounds for z, think about the region in which x and y will be allowed to vary in. Okay, so if I project my solid down into the xy plane, I'm going to get this sort of curved triangular region here. So I have this piece of the square root function here, then I have this horizontal line y equals 1, and then I have this portion back here of the y-axis. So in other words, I'm looking at this region here. So we're going to fix a point xy in that region. So think about, here's our point xy, and this is fixed for the moment, and now we're going to let z vary. And where is z going to vary? Well, we're starting down here in the xy plane when z is 0, and then we're just going to go straight up until we hit this face, this flat portion, in other words, until we're on the plane. So z will vary from 0 up to the height on this plane, z equals 1 minus y, so these will be our bounds. Okay, so for our integral, we're integrating our function f, and we're specifying the bounds for z. Z goes from 0 to the plane when z is 1 minus y. All right, great. So now let's think about letting x and y vary. Okay, and since the order is dy dx, this says now let y vary. Think about x as being fixed. And so if we're going to let y vary, that says fill out this region here with vertical strips. Okay, so if I imagine x being fixed for the moment, y would vary from the square root of x out to here when we're on just this horizontal line when y is 1. So these are going to be the bounds for y. Okay, and now to fill out this region with the vertical strips, we're going to stack those as we let x vary from 0 to 1. All right. So those are the bounds on x, and that is our setup. All right, the second order here, this is part B, dy dz dx. Now we're going to let y vary first and think about x and z as being held constant, okay? So for this, what we want to do is think about projecting our solid onto the xz plane now, okay? And this curve of intersection between the cylinder and the plane is going to get projected onto this profile curve here. It's going to look kind of roughly something like this. You have to think about just pushing this onto the xz plane, and we're going to get this kind of shape like this. And so then the region that we're going to let x and z vary through is going to be just the region bounded by this green profile curve, and then the x and the z axes, okay? Now what's the equation of this profile curve? Well, as I said, right, it's the curve of intersection for the cylinder, y equals the square root of x, and the plane, z equals 1 minus y. And so if I set y to the square root of x in this equation here, z is 1 minus y, I'm going to get this relationship between x and z for this profile curve. Okay, so now what are we going to do? Well, we're going to fix a point in this region here. I'll call this point, say, xz. So here's our point. Oops, not y, xz here. And now we're going to let y vary, right? So where will y vary between? Well, it's going to vary between, going to come out here. We're going to first hit the this face here, this curved face on the cylinder, and then we're going to go out until we hit the plane. Okay, so in other words here, y will vary from the cylinder when y is the square root of x out to this spot right here when y is what? When y is 1 minus z. Just rearranging the plane equation to solve for y. All right, cool. So for a fixed xz, y varies from cylinder to plane. So let's go ahead and write that down. Just got my integral of my function. And now we're specifying the bounds on y, and y is varying from the cylinder, which is root x, up to the plane when y is 1 minus z. And now we're going to let x and z vary through this region. And since the order is dz dx, this says now let z vary. So again, we're going to use vertical strips. So let's go ahead and set that up over here. So for a fixed x, we're going to let z vary from 0 up to this green profile curve when z is 1 minus the square root of x. So for my dz, I'm looking at these bounds. 0 up to 1 minus the square root of x. All right, and now to finish, we're going to go ahead and let x vary from just 0 to 1, because if we're going to fill this region out with these vertical strips, right, we're going to stack them as x varies from 0 to 1. So those are the bounds on x. And that is going to do it. All right, thank you so much.